Okay, and thank you for having me. It's very nice to, at least online, talk to you all. Okay, so what I wanted to talk about today is this idea of like expansions, expanded degenerations, and how it applies to problems for Hilbert schemes of points. So I'm going to, actually, before I start, if you want to have the notes for the talk, they are on my website. If you like look up my name and go under research on my website, there's like a list of talks. If you click on the talks from Munich last week, it's basically similar notes in case you don't want to take notes but want to follow what's going on. Okay, so yeah, please interrupt me if you have questions, if I'm going too quickly, if I'm not making sense. So I'm going to start by just telling you basically the aim of the project, what I was trying to do, and then I'll kind of, which will be very vague, and then we'll go into details of what it actually all means. So very briefly, the aim is what I've written here. So it's to construct this good degenerations of Hilbert schemes of points over semi-stable degenerations of surfaces. I've been deliberately vague with the word good here. We don't really know what it means yet, but some kind of good notion of these things. And the motivating example that I had when I started this work was thinking about Hilbert schemes of points on maximally degenerate K3 surfaces. Basically, because so this is, if you look at kind of like the moduli space of K3 surfaces and you look at the boundary of this moduli space and some compactification, and kind of like the worst type of degenerate K3 surface is this like maximally degenerate K3 surface. And how do we construct Hilbert schemes of points over those things? So that was kind of the original motivation, and this is kind of an interesting question, a question we care about, because Hilbert schemes of points on K3 surfaces form one of the only known, there's only like 4 known deformation classes of hyperkähler manifolds, and this is gives us one of the classes, so this is quite an important example to think about. Okay, so this is kind of vaguely the main motivation, reason why I wanted to work on this. So I'll give you some more detailed explanation of what we're actually doing, what we're actually working with now. So we start with this setup that we have this family X over C, where C is some curve isomorphic to an affine line. We're over some algebraically closed field of characteristic 0, so you can just think of the complex numbers. And we want this family X over C to be some flat projective family of surfaces. And basically throughout this thing, we're just going to consider some état local models. So we'll just look at some local picture and work with this kind of much easier thing here. So where we place some état local coordinates and we play around with this. So this is really kind of how we want to think of our family. So this spec K, X, Y, Z, T, quotiented by X, Y, Z minus T. So what that gives us is basically some family of surfaces where the general fibers are smooth. So like in the K3 situation, it would just be smooth K3 surfaces. And then this special fiber, so this fiber X0 over the 0 point in C. This has singularities, and they're like simple normal crossing type singularities. So in this état local model that we're considering here, we have over the point 0 in C. So when T is 0, we have just X, Y, Z equals 0. So we can picture this as these like 3 planes here intersecting transversely in A3. So basically just like a corner, basically like these 3 planes that intersect transversely, and they're given by X equals 0, Y equals 0, Z equals 0. Okay, so this is just kind of the basic object that we're working with. We just have this little family of surfaces and then this singular fiber that looks like these 3 planes. Okay, and then what we want to do actually is to say, well, let's take this family X and we remove this special fiber. So I cut that out. and I have some open thing, and then this thing lives over the punctured disk. So this, I keep doing this. This curve C where I've removed 0. And now I can rephrase what I was trying to do. So I can rephrase the aim of this project in terms of compactifying. So I can say actually what I'm trying to do then, given this setup, is I'm trying to construct some good compactification of the relative Hilbert scheme of M points written down here. Okay, so this, relative Hilbert scheme of M points. So we mean in each fiber of this family X, we look at the Hilbert scheme of M points of that fiber. So length M zero-dimensional subschemes in that fiber. If you're not very comfortable with these ideas of the schemes, if you're like a master's student or something, or like starting your PhD, or like the whole Hilbert scheme thing is a little bit hard to think about, you can just consider for this talk, just think about like collections of M points in each fiber. And then these M points like move in families over this curve C. So we have these M points or length M zero-dimensional subschemes in each fiber, and they're moving in families over this base curve. And then as we arrive at the point 0 in C, I've cut out the limit. So we have these families, and then they have no limit over 0. So I've just removed that. And I'm asking the question, how can I compactify? So how can I add back in this limit over 0, but kind of in a nicer way? Okay. Okay, so this is just what I was saying. Okay, so now I've been saying good, nice a lot, and maybe I should explain what I mean by this notion of good. What are we actually trying to do with this compactification? So clearly, kind of what I've been implying is that the just naive compactification, where you actually just add in exactly what you removed, like you don't actually change anything, this somehow is not good enough. And I want to make something like better. So what am I actually trying to do? So there's kind of two main perspectives that you can take. There's two main meanings of good that we'll consider in this talk. So firstly, this kind of hypercalar perspective, which was the original motivation, which is to say, well, let's consider that X over C is a type 3 or maximally degenerate. It's the same thing. Maximally degenerate, good degeneration of K3 surfaces. So if you're familiar with these things, I mean good here in the sense of these Kulikov models. So they will be like semi-stable models. But anyway, this is not very important. You just consider X over C to be some degeneration of K3 surfaces that is maximally degenerate. And you ask the question, can we construct some type 3, some maximally degenerate degeneration of Hilbert schemes of points on K3 surfaces, which also satisfies some good properties, so which is minimal with respect to the minimal model program. And in this context, this means this will mean DLT minimal, so divisorial log terminal, as a scheme, or like we can make it be semi-stable as a stack. So essentially what we're saying here is if we take this naive guy here, this guy is not minimal. And the reason it's not minimal is because basically the singularities are too bad in there. And we want the singularities to be less bad, but then if you try and resolve the singularities, you run into issues, because when you resolve the singularities, you might be adding in divisors, and then this essential property of the hypercalar variety, which is it has trivial canonical bundle, and this is comes from the fact that it has this everywhere non-degenerate holomorphic 2 form. This will maybe break if you resolve the singularities in a bad way. So you have to. So this is kind of a non-trivial question of how to actually produce one of these models that makes sense. Okay, so this is why using this expanded degeneration machinery that I'll explain later is a good idea in this context. Okay, and then the second perspective, which I'm calling the moduli perspective here, is so this is what I'll focus on today because it's a little bit more involved, and actually all the results that we produce for this question here also apply to the hyperkähler question. Okay, so the question here then is to say, by a good compactification, I mean I want to construct some flat degeneration as a proper Deligne-Mumford stack. So I want it to be kind of like a good moduli space. And the crucial condition that I'm going to ask for is that I want the limit. What am I doing? I want this condition here that the limit of each family of length m zero-dimensional subschemes should have smooth support in the compactification. So precisely what that means is we have these families of length m zero-dimensional subschemes. As t tends towards 0, they're tending towards this this special fiber here, and you can have these points like I've drawn here on this picture. You can have these points here tending towards this singular locus. So this here is the singular locus of x0. And basically you don't want the points to land in the singular locus. You want the points of the support of these subschemes to land in the interior of some component. You want them to land in the smooth locus of some underlying surface. So the way that we make this happen in the compactification is that we actually say, well, x0 is not good enough as a fiber, so I'm going to replace it by some modification of x0. And this is what I'm going to do. I'm going to modify x0 and basically like add in these extra components in this way. Okay, this is a very naive picture. This is not how we'll do it, but essentially you want to add in some extra components so that then your little points tending towards this limit will land in the interior of these components. So that's what we're trying to do. And additionally, if we do this, we'll also have this phenomenon that if we basically have 2 points traveling at like different speeds towards the same limit. So here, for example, I'll explain more what different speeds means. It's a little bit of a vague statement, but for now, we imagine a point traveling at speed t here, and a point traveling at speed t squared here towards this point here in the singular locus of x0, and they would both land there. But if we modify x0 in such a way that both of these points land in the interior of some component, actually what will happen is that we'll have to add in 2 components and they will end up landing in separate components. So something like this, where in the limit you're not able to tell apart these families that were traveling at different speeds, in our compactification that we construct, just by looking at the modification, we will be able to tell exactly what families we had. So just these pictures of the modifications will recover all of the data of the families that we had. So essentially what I'm trying to say here is this compactification should be sort of stratified in a way that recovers all of this data of the families. So you should be able to look at the limit, the support of these limits in the compactification, and that should tell you exactly what's going on. Okay, so the reasons that we want to do this, it's kind of a nice moduli problem, and it also basically if it's nice for sort of cohomological computation, stuff like that. You get to think about Hilbert schemes of points on some maybe complicated smooth surface by degenerating it to simple irreducible components. Sort of like it degenerates, it breaks into these irreducible components, but that are simple to think about. And then you look at the Hilbert scheme of points on the interior of these components. It's easier to think about than the smooth things sometimes, or just, if we're looking at Hilbert scheme of points on something singular, This is quite hard, but if we can kind of add stuff in and then actually take all of the support of the subschemes to lie in these smooth loci, it can help us answer some questions of the like cohomology type questions or other stuff. And then obviously there's some enumerative geometry applications in Thomas theory and that kind of stuff. Okay, so this is sort of vaguely what we're trying to do. So I'll explain this a bit better with an example. So hopefully it'll make more sense. Okay, so we just take an example. We take some family here of length 5 zero-dimensional subschemes in our étale local model, and this subscheme Z. So I have it given by it's made up of these two components, Z1 and Z2, which are given by these equations. So I have x minus y equals 0, z equals 1. So that gives me one component of length 2. And then I have this one, x minus y squared, gives me a component of length 3. So remember this, the ambient family that we live in is has this equation holding for it. So we can kind of say here we have x equals y, so we replace it in this equation. So this is the part of the subscheme given by x squared equals t. Similarly, this is the part of the subscheme given by y cubed equals t. And this z is just constant to keep things not too complicated. And then the question I ask is, well, what happens as we approach this special fiber? What happens to this subscheme z? So as t tends towards 0, both of these components basically will tend towards the same point in x0, because as t tends towards 0, both of them tends towards x equals y equals 0 and z equals 1. So they'll tend towards this point here on the z-axis in the x equals y equals 0 locus. And so in this way, we can't tell them apart from this picture because they've landed in the same place. And essentially, this is what we're trying to change. So we're trying to say, well, actually, these two things were given by different equations, and I would like to make some modification of x0, which takes this into account, so that keeps track of the fact that we had different equations for z1 and z2. Okay, and what exactly this means, sort of more precisely, when I say we want to keep track of the fact that we had different equations, is I would say basically, the data we're trying to record with this is the degrees of vanishing of z1 and z2 in the x, y, z variables. So this is how we tell them apart. Okay. Okay. So basically, so the way that we will do this is by combining these ideas of tropical geometry and these ideas of expanded degenerations. Okay, so does anyone have any questions so far?
So in general, do you want to make sure that they go to each of the components separately? And is that what you're defining as a good degeneration?
Yeah, I want them to each land in the smooth locus of some component, and also if they're given by different equations, by different degrees of vanishing in the x, y, and z, they should land in different components. So I should be able to look at this modification and look where they land, and I should be able to just tell you it was this family. Like I can write down the equation just from looking at that.
Okay.
I don't know if okay. So cool. So before I go into what this tropicalization, expanded degeneration business means, previous work in this area is, and kind of the context for this project. So the method of expanded degenerations was first introduced by Lee in 2001. And then in 2011, Li and Wu, they used this method to construct good degenerations of quad schemes over families where we have this restriction here that the singular locus of x0 should be smooth. Okay, so they managed to use already these techniques for quad schemes, but they have this significant restriction that they have to have this singular locus of x0 is smooth. So for example, in a case like ours, where this is our special fiber, this is our singular locus, we don't fit into this description because we have this singular point in our singular locus. So their techniques will not apply to the question we're asking. But nevertheless, in a kind of simpler case, they are able to do this. And then in 2017, Gulbrandsen, Halle, and Hulek basically described this GIT analog of the Li-Wu construction. They do this specifically for Hilbert schemes of points because they're trying to show basically how this stuff works for the K3 surface case. And if you have this restriction here that Li and Wu have, and that they have again, you're not in the maximally degenerate K3 case, but you're in the type 2 degeneration case. So it's sort of the slightly less degenerate case. And then they managed to show actually GIT is a very nice thing to apply to this problem. And actually the thing that they construct ends up being the same thing as the Li-Wu thing. So this kind of all works out very nicely. And they have the second paper then with Yu Zhang in 2020, where they work out more of the stuff to do with the hyperkähler perspective. Okay, so in this context, there are a lot of solutions to this problem, given this specific restriction, which is quite a big restriction. Not many families will look like that. So this is, it works well, but it's very limited in that sense. And then slightly more recently, in 2020, we have this work of Maulik and Ranganathan, where they use logarithmic and tropical geometry to construct good degenerations of Hilbert schemes for some families where the special fiber can have any type of simple normal crossing singularity. So this is hugely more general because anything that you can kind of get into the simple normal crossing setup by using semistable reduction, then you could apply this machinery to. So this is kind of really opens a lot of doors. And then, the last thing to mention is last year, Kennedy Hunt extends the Maulik-Ranganathan construction to quad schemes, and he gives kind of a more canonical way to think about the problem, which I will maybe come back to at the end if I have time. Okay, so this basically is what has been done in the area before, and maybe when you've seen this, the question to ask is, well, what are we doing? Like, why are we trying to solve this problem when it looks like Maulik and Ranganathan have already solved it? They do this for any type of simple normal crossings. So the thing that we're looking at is included in this, obviously. So why are we still trying to solve this problem? And the issue is that, like, yes, they do solve the problem, but what happens is that they give an infinite family of birational solutions, and there is no way of kind of sorting through this. So there is no kind of sense of like a better geometrical model, or like what these things mean, how they relate to each other. And especially we have no explicit example of one of those things. And it's from their work, it's quite hard to see how to construct an explicit example of one of these degenerations. So it's kind of, it shows you that you can do it, but we don't really know what one of these looks like, which obviously is kind of a problem. So so that's basically the question that my work tries to solve is, let's actually construct some explicit examples. Let's show that they are geometrically meaningful examples of the Maulik-Ranganathan stacks and discuss the hyperkähler perspective on them. Okay, so before I tell you what I did, I will discuss a little bit how this whole tropical geometry perspective can be used here, because I think it's actually like a very nice way to think about the problem. It's a very nice way to visualize what's going on, and I'll describe a little bit what Maulik and Ranganathan did in their paper and kind of the limitations of those methods, and then I'll get on to say how I address those. Okay, so what are we doing with this whole tropicalization business? So essentially, in the example that we were looking at before, I told you that the data that we're trying to record, so when we're making these modifications, I'm trying to keep track of these families, and that data is specifically the degrees of vanishing of the families in the X, Y, and Z. So in these étale local coordinates. Okay, so this is what I'm trying to record, and basically tropicalization is an obvious thing to use here because it's exactly the object that parameterizes these degrees of vanishing. So what we do is that we build the tropicalization of X with respect to the divisorial log structure given by the divisor X0. And what this means is basically we're just saying, like at X0, we have the functions X, Y, and Z vanishing. And we're constructing the thing that parameterizes their degrees of vanishing. So so we take this fiber X0 like this. So I've labeled the components Y1, Y2, Y3 for convenience. And then to each point in this fiber, I'm going to attach a number of copies of the natural numbers. And this number of copies will be given by the number of functions vanishing at that point out of these X, Y, and Z. So, for example, if I take a point here, well, I have just X vanishing here, Y and Z don't vanish. So I attach one copy of the natural numbers. Similarly here, in this intersection locus where X and Y both vanish, I attach two copies of the natural numbers. So you should think of these natural numbers as being exactly the degrees of vanishing in X, then the degrees of vanishing in X and in Y, because we have these two variables, it's two-dimensional. And then at this triple intersection point where X, Y, and Z all vanish, then I can consider degrees of vanishing in all three variables. So that gives me some three-dimensional space. So I attach a copy of N3. And this kind of vaguely stated is basically the data of the tropicalization. So if we just go over to the tropical side and we draw what X becomes, well, if I look at my Y1 component, that should become something one-dimensional in the tropicalization, because it's just given by N. So it'll be this, so I'm abusing notation here and calling things Y1 and so on. Again, on the tropical side, so Y1 from the geometric side becomes this one-dimensional half line on the tropical side. Similarly, Y2 and Y3 will be one-dimensional on the tropical side, so they become these half lines here. Then this intersection locus here of Y1 intersect Y2, this should be two-dimensional. And it'll be this here, this two-dimensional this two-dimensional face of this cone between the Y1 and the Y2. Similarly, Y2 intersect Y3 and Y1 intersect Y3 will also be these two-dimensional faces here of the cone. And then this triple intersection point here in the middle, this will become something three-dimensional as the three-dimensional interior of the cone on the right-hand side. Okay, so this is the basic picture to have in mind for this kind of tropical setup. And actually, to kind of simplify things, something that we can do is that we can actually just take a slice through this cone and just write down this triangle that I've drawn in pink. And this is basically just fixing some height in the cone. And then we can draw all of our pictures for this triangle. So it's kind of easier to think about. Okay, so yeah, so basically we fix the height and we allow ourselves along this, while we're working on this stuff, we'll allow ourselves to change the height of this triangle within the cone if we need to. And geometrically, this is basically just making some base change on our family. So if we need to make a base change on our family, we will modify the height of this triangle. I'll explain a little bit more in a moment about this. Yeah, and so, okay, so just to mention, so if you're familiar with talking about like the dual complex of something, then the triangle here is just a dual complex of this special fiber x0. Okay, so this is the tropical picture. So why do we care? So we'll go back to the example and we'll see how we can apply this tropical stuff to the example we were considering. So here, if we have, okay, so we have our family that I gave you before, Z, given by these Z1 and Z2 components. And basically what I want to do here is I want to compare the degrees of vanishing in the XYZ of Z1 and of Z2. And in order to do that, I need to make some base change so that I can write XYZ in terms of some power of some variable. So I make this base change t equals u to the 6 for some new variable u. And that allows me then to rewrite, so the same family, but written differently. So here I can write x, y, z as u to the 3, u to the 3, 1. And in the z2, which had x equals y squared, I can then write that as x equals u to the 4, y equals u squared, z equals 1. So I've kind of chosen u in an appropriate manner so that I can write x, y, and z for both components as some power of u. Okay. So this is just, me re-expressing the family z in some different way for convenience. And then if I do this, well, I can write down these vectors here, which are given by these powers that I have in this expression. And so we have 3, 3, 0 and 4, 2, 0. And basically what we're doing with the base change is that we're placing this triangle. So this is the triangle here that we had in pink before. We're placing this triangle at an appropriate height inside the cone of the tropicalization of x so that the points 3, 3, 0 and 4, 2, 0 land on the triangle. That's all that we're doing. So we've done that, and then we can write this kind of image of the subscheme inside the tropicalization of x, like this. So we write these 2 points on the triangle, and doing this actually, adding these vertices to the triangle gives us some modification of x0. So if you see here, like the vertices in the triangle correspond to these two-dimensional components in the fiber on the geometric side, and basically adding these two vertices tells us you have to add two new two-dimensional components in this fiber. They will fall between y1 and y2, and this is where the limits of z1 and z2 fall inside of these new components. So if we make this modification exactly in the way that the tropicalization tells us, then we have that these limits of z1 and z2 will land exactly in the interior of these different components. So this is telling us exactly how to answer the question that we were asking before. How do we modify this special fiber so that we have this condition that we want holding? So this is exactly what you do. So that's good. However, we have some problems with this. So the first problem is that, I'll go a little bit more quickly through this. The first problem that we have is basically, okay, so this is a nice solution. For each z, we've constructed some modification, but that's kind of also the problem. For each separate z, I've constructed a separate modification, and I have no idea how these modifications all fit together. I'm not trying to construct loads of different objects. I'm trying to construct one coherent object, one degeneration. So how do I fit all of that together into a large family? And this in Maulik and Ranganathan, it can be done, but it's actually very non-trivial, and there's a lot of choices involved in doing that. And it's not obvious what that would look like in an example. And then the second problem, which is also a big problem, is that these modifications that I've made are kind of weird. They're not blow-ups. They're stuff maybe where I've blown something up and then I'm contracted part of it in order to get like just the right amount of added stuff, added components. But the problem with this is that we're trying to fit everything. We're trying to embed all these modifications into one big family to show how they all relate to each other. And contracting stuff all over the place means that this big family will not be flat. So this, we're in trouble. This is not geometrically nice at all. And in order to make this work, basically, Maulik and Ranganathan then say, well, okay, so we've contracted stuff where we shouldn't have, so we have to add that stuff back in. But then we've added a lot of components that weren't there before, and then that adds more limits, and then that breaks separatedness of the stack we're trying to construct. They have to add another stability condition on top of the one that they already had. So this is where they add this, like, oops, what did I do? This is where they add this, like, Thomas stability. And so there's a lot of steps you can do to fix this and make it work, but it involves a lot of different choices, and it's hard to see what you end up with, basically. Okay, so the way that I address this is to say, well, okay, let's try and build some examples of these things. Let's see what they can look like, and we start with methods closer to the Li and Wu and the Gulbrandsen, Halle, Hulek methods, which are to say we start by taking this family of surfaces over my curve, and I say, well, I'm just going to start by enlarging the base. So I want to give myself much more space. I want to give myself a bigger family. So I just take some fiber product like this. I make the base way bigger, and then in this fiber product here, I'm actually going to have, it's going to give me tons of different copies of the original fibers of here. So this in particular sort of includes lots of copies of the special fiber X0. So I will have lots of copies of X0 living in this big family, and then I will be able to make modifications to X0 inside of this family, hopefully in a nice way, so that I have all the modifications I need and I have some kind of coherent problem. Okay, so the way that we do that is to say we have this big family, and then we make some sequence of blowups, and we call this resulting space xn after all these blowups. And these blowups basically will be, they won't change anything in the general fibers, and then in the copies of X0, they will give you modifications of X0. And it's kind of subtle how you have to choose these blowups. It's not at all obvious how you do it, but basically, you want to kind of, you want your blowups to be chosen in a way so that they commute with each other, and so that you kind of have your structure of your space. You need kind of the space to have some structure that makes sense in terms of how the limits of the different subschemes relate to each other. Okay, so essentially the blowups that we make are the following. So so if we have an element in this enlarged base, we call its entries Ti. We allow ourselves to make, so we're kind of very restrictive with the choice of blowups we allow ourselves to make. And we say I can only make stuff that is a blowup along the ideal X and some Ti, or Y and some Ti, or Z and some Ti. So yeah, we only allow for these like very specific types of blowups to happen. So I've drawn them here on the tropical side. So blowing up X is like blowing up this Y1 component. So it kind of here you can see, like on the geometric side, it adds this P1 bundle over the intersection all around Y1. On the tropical side, this is just adding kind of this component here between Y1 and Y2, this component here between Y1 and Y3, and the intersection between them here is this edge between the two. So this, we're allowed this picture, we're allowed this second picture or this third picture. And actually a crucial thing to say is you only need to allow for 2 of these types of blowups. And actually allowing for all 3 of them is a problem. It actually doesn't work nicely. You're not able to make the problem work. So in order to make things work, we actually have to break the symmetry and say, well, because it actually, we are able to construct enough modifications to make the problem work with only 2 of them. So say arbitrarily, I choose these 2 ones. Because I'm able to make the problem work with these 2, actually the problem won't work if I try and take more stuff. And I have to restrict myself to just use these. So I use these and I combine them together. So this is kind of this crucial step that we have to actually accept, that we need to break the symmetry of this construction to make it work. And then the way that I chose the blowups means that these, you know, if you blow up in X and then in Y, it's the same thing as blowing up in Y and then in X. And everywhere that we do this, these blowups will commute. So kind of the modifications embed into the big family in many different ways, and that allows for all the limits we construct to relate to each other well. Okay, so I'm sorry, this is like slightly vague because it's kind of non-trivial, but it's, yeah. Anyway, so this is essentially kind of the difficulties, how we address them. And then I'm going to wildly just skip over the stuff that comes after it, basically, because there's no time. So yeah, basically what we've done is that we've constructed this big family here, xn, which is some sequence of blowups on our fiber product here. And yes, so this is a massive family and it has loads of different modifications. It has all the modifications we need inside of it, but it's huge. And we need to kind of squish things back down because we're trying to find a degeneration over a curve. This is too big. So we add some group action to this thing, which essentially does several things, but essentially just squishes everything back down into some one parameter family. And then I have to make things into a stack like this. So I take the group action, I make a stack. And this, I won't go into details of why it happens, but essentially, yeah, the stack setup has to do with this need we have to do base changes. So in order to represent these limits, I need to allow myself to make these base changes to change this like height of the triangle and the cone. And so I need to be talking in the stack setting and not in the scheme setting. Okay. Okay, but this, you know, maybe it's not super important right now. Okay, so we do all of this, we get this stack X, and this is some object that contains all of these modifications that we've made in order to represent our limits. It contains all of our original fibers that we had in our original family. And then with this, I can prove this following theorem. So this says the stack of Liu stable length M zero-dimensional subschemes in this X is Jane-Mumford and proper over C. And obviously, by construction, it will have all the properties that we wanted it to have. So this is kind of, this is a very surprising thing that happens here, actually, because here we are able to just take the stack X and apply kind of the simplest stability condition you can apply in this type of problem, which is kind of the original stability condition from Li and Wu. And this tells you actually there's nothing else to do. Like if you do that, you're already finished. You already have a stack which is proper and everything works out. And this is very surprising because the Maulik and Ranganathan paper, so like I wrote here, they predict that in general this is not at all what happens, because they predict that in the general case, whatever you do, you will end up with something which is actually universally closed but not separated if you're just using this Liu stability. And then you have to mess around and add some additional Donaldson-Thomas stability or some analog of this. But Liu stability on its own normally should not be enough. But here, because we've made such like specific geometric choices, actually this picks out like a very special example where Liu stability is actually just enough on its own and there's nothing else to do. So this is kind of interesting from that point of view. It's quite a special example. But clearly, okay, it's not what happens in general. And we can ask the question also, well, what does happen in general? So then I kind of explored taking a larger stack X dash, which contains our original stack X as a substack. And this larger stack, basically, you're just allowing more choices of modification of X0 to live in there. So it's the same thing where you're just saying, I'm just throwing in some extra modifications, and then I'm seeing what the possible limits of all the families are if I allow for more stuff. Okay, so clearly here I've thrown in extra modifications. That throws in extra limits to all my families of length m zero-dimensional subschemes. And so typically for a family, now for a family Z that I'm going to choose, there will not be a unique limit. There might be several limits for a given family Z, like the one that I showed before. So this is a problem because our stack then is not separated. So our Liu stable stack in this case is not separated. This is what we expect to happen. And then I kind of have two ways that you can solve this problem. So kind of depending on what you care about, the first way is that you can say, well, okay, my limits are not unique, but I'm just going to say, well, I don't care about that. I want the most canonical thing that you can do. So for each family Z, so you have like some family like we looked at before, it has several limits, and I say I take an equivalence class which identifies all of these limits. So this is kind of, even if the limits are not isomorphic, I'm just going to take some equivalence class and identify them, and my stack will parameterize no longer subschemes, but equivalence classes of them. So this, you can do it, and then you recover some proper stack, but it will be non-algebraic. So it depends what you care about. You know, this is the most canonical object, but difficult from this point of view. And this parallels the work of Kennedy-Hunt. So this is what Kennedy-Hunt does for his logarithmic quad scheme construction. Only his is even more general because I'm still making some geometric assumptions in the construction here, whereas he says literally allow any modification to happen. Everything gets identified. It's the most canonical thing. Okay, so that's what he does. Okay, so this is one solution, but maybe you want still to have algebraic stacks. Maybe non-algebraic is a step too far. So in that case, what you do is more similar to the Maulik-Ranganathan solution, where we basically add some extra stability condition. So here, this stability condition is the analog of the Donaldson-Thomas stability condition in the Maulik-Ranganathan. It's not exactly the same thing just because I've kind of done my construction in a completely different order, so you end up having to do different things at different stages, but it serves the same purpose, and kind of it's quite subtle to analyze how exactly to set up the stability condition. But essentially you can set some stability condition to cut up some proper substack. So here you're saying, for my family Z, I had several limits, and I will make only one of them be stable, and all of the other ones will be unstable, and I'll throw them away. And if I do that, then I recover some choice of Maulik-Ranganathan stack. Not all choices can be recovered in this way because, like I said, I'm making some additional geometric assumptions in my stack X dash as well, but it will recover some kind of like geometrically meaningful examples of these stacks. Okay, I think I will stop there and allow some time for questions. But thank you for listening.